Hello everyone. Today we are going to study the VI characteristic of PN junction diode in both forward and reverse bias. Okay, so in that case, the main apparatus will be needed are a PN junction diode, a regulated power supply, ammeter, voltmeter, connecting wires, one breadboard, and one resistor. Okay, here you can see that this is a PN junction diode, and you can see that this is the P region and N region, and between the P and N region there is a depletion layer. Okay, so when this PN junction diode are connected in both forward and reverse bias, their VI characteristic will be different. Okay, now what is the main theory behind that? When we are connecting the forward PN junction diode in forward bias, the width of the depletion layer is getting lesser, but when we are connecting it in reverse bias, the width of the depletion layer is getting thicker. Okay, now here the two circuit diagram in forward and reverse bias are shown here. You can see that this is the battery positive and negative terminal of the source, and here you can see that the battery is connected to the positive terminal of the diode via resistance and milliammeter, and the negative terminal of the battery is connected to the N terminal of the diode, and here you can see that the millivoltmeter is connected in parallel combination with the diode. So in the milliammeter you will get the forward current, and in the millivoltmeter you will get the forward voltage drop across the diode. Here in the reverse bias, similarly, the connection is same, only you have to connect negative to positive of the diode and positive of battery to negative of the diode. And one more difference is that in forward bias we are using milliammeter, but in reverse bias we are using microammeter, because we know that in reverse bias the current in the circuit in the PN junction diode is very lesser, in the microampere range. And here to measure the voltage drop across the diode, we have connected millivoltmeter similar to that of the forward bias, and what we have to do is that we have to vary the source voltage from 0 to 30 volt in one voltage step in both forward and reverse bias, and we have to measure the current and voltage in both forward and reverse bias. So now what is the model graph in both forward and reverse bias of a PN junction diode? Here you can see that this is the current voltage graph. Here you can see that the x-axis is the voltage axis. So this is the forward bias voltage, and this is the reverse bias voltage, and the y-axis is the current axis. This is the forward bias current, and this is the reverse bias current. Now there is a difference of the forward and reverse IV characteristic graph. Here you can see that the IV characteristic graph is increasing slowly after a certain voltage, and that voltage is called cut-in voltage. So from the graph we have to determine what is the cut-in voltage of the particular PN junction diode, and you have to also calculate the forward dynamic resistance and reverse dynamic resistance from the IV characteristic graph. You have to take two different points after the cut-in voltage exactly on the IV characteristic graph, and we have to calculate the delta IF, that means the difference of current in that two particular point, and at the same time the difference between voltage on the voltage axis corresponding to that two particular point. So the forward dynamic resistance is equal to delta VF by delta IF, and similarly the reverse resistance also we can calculate by taking 2 points on the reverse characteristic IV graph, and the value of the dynamic reverse resistance will be delta VR by delta IR, and the unit of these two parameter will be in ohm. Okay, so this is the table in both forward and reverse bias. Here you can see that the first column is serial number, and the second column is the source voltage, that means the voltage we are giving to the diode in both forward and reverse bias connection. Now this is the IF, that means the forward current, and as we know that we have connected milliampere, so the unit will be milliampere, and we have to convert the milliampere current to ampere. And similarly the voltage drop across the PN junction diode, you will get it from the millivoltmeter, and you have to convert to from millivolt to volt. So that's why this is the forward voltage drop across the diode. Similarly, in the reverse bias also, you will get different reverse current in microampere. You have to convert from microampere to ampere, and you will get voltage drop across the diode in millivolt, and you have to convert from millivolt to volt. So first you have to increase the source voltage from 0 to 30 volt in a step of 1 volt, and then you have to measure the current and voltage drop across the diode in both forward and reverse bias. Okay, now how you can measure the voltage and current in both forward and reverse bias. Now I will tell you what is the circuit diagram, and what are the main apparatus, how it will look like, the circuit diagram, and how you can connect the circuit in both forward and reverse bias. First of all, I will tell you what is the forward bias circuit. Here you can see that this is the regulated power supply. Here this is the source voltage. It is showing in a digital display meter, and the red one is the positive terminal of the battery, and the black one is the negative terminal of the battery. Ground, the blue one, but it is green one, but it is not used today. Okay, this is the main power button here. So if you switch on the power button, you will get light in the display in both voltage and current, but the voltage will be only used. Here there are three different buttons you can see. The first button, this one, is for the overload button. If the overload light is on, then by adjusting this button you have to switch off the red light here. If the light is not glowing, that means the circuit diagram is properly connected. It is not overloaded. Now the second button here, this is the voltage variation button. By changing this, to change the voltage, you have to vary this button like this. You can increase the voltage. Suppose this is 3.6 volt. Now you can increase to 4 volt and 5 volt up to 30 volt. Okay, so initially it will be 0. And the third button, this button is actually the voltage fining button. That means if the voltage is not initially 0, then you have to adjust this button. Otherwise it should not touch this button if it is 0 already. Okay, now this is the connection you can see here. This is the 1K resistor connected in series with the battery, and this is the PN junction diode. I will show you how you can determine the P and N terminal of a PN junction diode. Here you can see that the left side is a black strip. That means this black strip side is always N side or negative side, and the other side is positive side. That means the black strip side is always N and the other side is always P region. That means the positive region. So here we have already inserted the PN junction diode in the breadboard. Okay, and we have connected this circuit diagram in forward connection. And here this is the milliammeter which is connected in series with the battery, and this is the millivoltmeter which is connected in parallel combination with the diode. So from this millivoltmeter we can measure the voltage drop across the diode, and by changing this voltage we have to take the measurement of both current and voltage in forward bias. Well, now this connection is a reverse bias connection of the PN junction diode. Now what are the main difference of forward bias and reverse bias? In forward bias we have used a milliampere in forward bias, and in reverse bias we are using this microammeter in series with the battery. Now why we are using this microammeter? Because the current in the reverse bias is microampere range, that is very close to 0. So that's why we are using the microammeter in series. Now what we have to do, the similar thing we are doing here in reverse bias also. We have to increase the source voltage by changing this button. So first it is 0 initially, and we are getting that the current in the microammeter is also 0. The voltage drop is also close to 0. That is actually, that should be ideally 0. Okay, now we have to increase the source voltage here. So suppose we are increasing it to 1 volt, then we can see that the fluctuation is very small. That is close to 2 microammeter. Actually very less current we are getting. And now when we are increasing it to 3, the fluctuation is also very small, and the voltage drop is now getting increased a little bit in the reverse bias. And similarly you have to take the voltage at 3 volt source voltage, and accordingly you have to measure the microammeter reading and millivoltmeter reading connected in parallel. And finally you have to take at 20 volt and corresponding microammeter reading and millivoltmeter reading. So this is the process, and we will get another set of data in reverse bias connection by varying the source voltage from 0 to 20 volt in 1 volt step, and at the same time we have to measure the current in microammeter, and we have to convert it from microammeter to ammeter, and the voltage we have to convert from millivolt to volt. So we are getting two sets of data, one in forward bias and one in reverse bias, IV characteristic data, and we have to plot the IV characteristic graph in forward and reverse bias, and we will get a graph like this in forward bias, which the slope is much more steeper compared to the reverse bias graph. And from that graph we have to calculate the forward dynamic resistance and the reverse bias dynamic resistance, and at the same time in forward bias you have to determine what is the cut-in voltage of this particular semiconductor. The calculation part, I already told you that the dynamic forward resistance and dynamic reverse resistance will be calculated from the IV characteristic graph So these are the formula. RAC for forward resistance is delta VF by delta IF, and you have to calculate, the unit will be in ohm, and the dynamic reverse resistance will be delta VR by delta IR, and the unit will be same, ohm. Okay, now from this experiment, what we can conclude? We can conclude from this experiment that the forward dynamic resistance is lesser, but the reverse dynamic resistance is comparatively larger in the kilo ohm range. So that we can say that the current in the reverse bias is very lesser, almost close to zero, but in the forward bias the current is very high. So that means in a PN junction you are getting forward bias current only. In the reverse bias you are not getting any current, or if we get any current, that current is very small value. Okay, so that means the diode is acting as a unidirectional semiconductor device. So that means it is acting as a diode. So this is the conclusion. Now, what are the main applications of this PN junction diode? We know that a PN junction diode, because of its forward bias characteristic and reverse bias characteristic, it can be acted as a rectifier, and also it is uses in different switching technology in digital logic designs. That's it. Thank you.